before we get started, I'm going to write this divide statement in modular arithmetic form. This is from a number theory book. It was published way back in 1970, I think, by Sierpinki. Now, the way you'd see this in modular arithmetic, a way you could see it, not necessarily the best way, it's this is not congruent to 0 mod n. Now, what do we mean by mod n? When you divide this expression by n, what remainder do we get? Now, if it was equal to 0, it would be this would be a multiple of n, okay? But we're looking for the least integer, and it to be a positive integer, I guess, such that n does not divide this quantity. Now, and the way they typeset back then, for whatever reasons, they didn't put parentheses, but in my opinion, for readability, the parentheses belong there. But we're looking for the least integer n such that n does not divide this, but it does divide 3 to the n minus 3. Okay? So let's carry on here. There's a kind of an interesting way that's based on the logically equivalent contrapositive. This statement right here, n does not, just the given statement implies n cannot be prime. And we'll get down to that in just a minute. But another name for this, n is not prime, means the very same thing as composite. Okay. And so this really gives us quite a bit of information if you believe it. It's really kind of the contrapositive of Fermat's little theorem of special case. Okay, and that's what I've shown you right underneath this. Y'all remember, this is in the form A implies B right here. A implies B. Okay, but notice that what I've done right here, this is not B, and I'm going to just use a little thing for negate. I don't know if you put it above or below. I don't have room to put it above. But not B also implies not A. They mean the same thing, and sometimes one is easier than the other. Now, a way to get a grip on this thing right here, if it is raining, the ground is wet. If the ground is not wet, it's not raining, right? So those two things mean the same thing, essentially, logically at least, okay? Now notice right here, this is an easier thing to work with. N is prime implies this, and this is simply Fermat's little theorem. If you take a look right here, a to the p minus a is congruent to 0. Okay, mod p. You may be used to seeing the A on the other side. Now, I refuse to call it, N is prime. I'm not going to call it little p like a lot of people think you have to. Okay? But anyway, this statement right here is equivalent to this statement right here. Okay? Now, so that's pretty big. N is not a prime, so we look for the first non-prime integer, or the first composite integer, which is 4, and we check it. Okay, so where are we checking it? Well, we're checking it back in this original, right? So we take this 4 and put it here. You get 2 to the 4th is 16 minus 2 is 14 right here, right? And so this 4 doesn't work because it's a does not divide in both cases. Okay, again, you can check if you put a 4 here, you would get 3 to the 4th is 81. 81 minus 3 is 78, right? So it doesn't work. We know it has to be, n has to be composite. You see, that's kind of a big deal. I didn't figure this out. I had to look at the solutions. It's a nice little filter here. You just look at composite solutions. So we got to skip 5, and now we'll try 6, okay? Now let's see here. 6 does not divide, and you can check here. 2 to the 6th is what, 64? Minus 2 is 62. Right, folks? Again, I put the 6 right here. 2 to the 5th is 32. 2 to the 6th is 64. 64 minus 2 is 62. And 6 certainly doesn't divide that. Okay? But notice that 6 does divide. Okay? 3 to the 6th, folks. that is, let me just write this down. 3 to the 6th minus 3. All right. Now, this is the same thing as 6 divides 720, right? I do the arithmetic right, folks. 3 to the 6th, 3 to the 4th is 81. 3 times 81 is 243. 3 times 243 is 729. Oh, that should be 726 right there, folks. My bad. 726, not 720. So this is 726, bold, right, folks? Again, this is 729, isn't it? Just documenting the arithmetic. 729 minus 3 is 720. And 6 certainly divides 720, because it divides 720, right? 120. So this is actually 6 times 121 is 726. So 6 is our answer, folks. 6 is the answer, because we get a does not divide here just like we want, and we get a does divide here like we want, and it's the very first integer. So the least integer would be 6. And I really like this part here a lot, where it's something obvious, but this statement right here is fairly important because it kind of filters out the values you can search for. Okay, you don't check, no prime number could possibly be a solution according to this, if you believe it. And it is just Fermat's theorem, the contrapositive of Fermat's theorem. There's 2 forms. A to the p minus 1 is congruent to 0, and then multiply through by a. It doesn't change anything. But anyway, this there's the relatively prime condition doesn't really matter on this one here, I think. But anyway, 6 is the answer. And y'all, I believe, again, in Sierpinski's book, he said, when you see a question like this, you expect what's the least one, then that means you expect there's either a finite or infinite number of such n. It turns out a harder proof is to show there's an infinite number of these type of n. This is just the least of those values. So again, think about that a little bit. I may try to produce a video on that. I think it's not a routine proof, though. It's not a routine proof as far as showing that there's an infinite number of composite n that satisfies this condition. If any of y'all know, let me know. Okay, I'd like to see the proof. I think it's just kind of I think it's slightly messy. I'm not sure if there's an elegant way to show it really. Okay, that's all.